Jai Shri Krishna. A very good and warm morning to everyone assembled in this virtual platform for today's webinar, organized by PG and Research Department of Mathematics, DG Vaishnava. It is my pleasure to welcome you all to this national webinar organized by PG and Research Department of Mathematics, DG Vaishnava College. It is mark of our undying tradition to invoke the Almighty at the beginning of all events. Let us begin today's webinar with the Tamil Thai Valthu, followed by our college prayer.
நீராறும் கடலொடுத்த நிலமடந்து எழிலொழுகும் சீராரும் வதனமென திகழ்வரத கண்டமிழே எக்கணமும் அதிசிறந்த திராவிடனல் திருநாடும் தக்க சிறு பிறை முதலும் கரித்தனரும் திலகமுமே அத்திலக வாசனை போல் அனைத்துலகும் இன்பமுற எத்திசையும் புகழ் மணக்க இருந்த பெரும் தமிழனங்கே தமிழனங்கே உன் சீரிழமை திறம் வியந்து செயல் மறந்து வாழ்த்துதுமே வாழ்த்துதுமே வாழ்த்துதுமே.
सत्यव्रतं सत्यपरं त्रिसत्यं सत्यस्य योनिं निहितं च सत्ये सत्यस्य सत्यं ऋतसत्यनेत्रं सत्यात्मकं त्वां शरणं प्रपन्नाः वाणी गुणानुकथने श्रवणो कथायां हस्तौ च कर्मसु मनस्तव पादयोर्नः स्मृत्यां शिरस्तव निवास जगत्प्रणामे दृष्टिस्ततां दर्शनेस्तु भवत्तनूनाम् ओ भगवते तस्मै कृष्णायाद्भुतकर्मणे रूपनाम विभेदेन जगत्क्रीडति यो यतः ॐ शान्ति शान्ति शान्तिः.
Now, I would like to invite Dr. S. Hariharan, Assistant Professor, PG and Research Department of Mathematics, the organizing secretary of today's webinar, to formally welcome this gathering. Over to you, sir. Dr. S. Hariharan.
Yeah, warm and very good morning to all of you. I take this opportunity to welcome all of you for this one-day webinar on NEVANLINNA theory and its applications. First of all, I would like to welcome our secretary, Shri Ashok Kumar Mundraji, our principal, Dr. S. Santosh Babu, and also the convener and head PG Research and PG and Research Department of Mathematics, Professor R. Venkatramanan. I welcome my department colleagues as well as the faculties joined from other institutes I also welcome all the students and participants for this one-day webinar by our chief guest, Dr. S. Rajeshwari. I welcome you all, and uh, we will make this wonderful opportunity to know something about Nevallina theory and its applications. Once again, I welcome all of you. Thank you.
Thank you, sir. Thank you for your earnest welcome address. Change is the end result of all true learning. The whole purpose of the education is to turn mirrors into the windows. Today we have with us Dr. S. Rajeshwari to deliver a talk. Now I cordially invite Dr. N. Jayant Karthik, Associate Professor, PG and Research Department of Mathematics, DG Vaishnava, to introduce about the speaker in this gathering. Welcome you, sir.
Good morning, all of you. Dr. Rajeshwari, currently working as Assistant Professor, the Department of Mathematics, Presidency University. She has over 13 years of teaching experience. She has published over 25 papers in reputed journals. She is currently guiding 4 students for PhD degree. She has served as a referee for international journals from Georgia, Italy, Korea, and UK. I request Dr. S. Rajeshwari to take up the session. Welcome you, ma'am.
First of all, let me thank the organizer of this webinar for giving me an opportunity to speak here. Today's my topic is NEVANLINNA theory and its applications. So the value distribution theory is one of the oldest topic of complex analysis. Perhaps the fundamental theorem of classical is the first well-known result on the value distribution of functions, and the next one is Picard's theorem. So value distribution theory of meromorphic functions, also known as NEVANLINNA theory, is the backbone of the present discussion. So in particular, this theory appeared to be a most powerful tool in investing analytic or meromorphic solutions of complex differential equations in the complex plane as well as in the unit disk. This theory mainly conveys the information about the rate of growth and about the frequency with which given extended complex values are taken by meromorphic functions. The classical theorem of Picard that a transcendental entire function assumes all finite complex values with at most one exception, which marked the beginning of extensive research in the branch of complex function theory, the field of exceptional values of entire and meromorphic functions. So Picard himself proved this theorem in 1879 by using the techniques of elliptic modular functions, and a significant step forward in this direction was the work of Borel in 1896. So Borel, by introducing the concept of exponent of convergence of an entire function, proved is a well-known and classical result. The exponent of convergence of the a points of an entire function of finite order equals its order with at most one exception. This result, generally known as Picard-Borel theorem, which led the foundation of the theory of value distribution. Later, another mathematician named Waleron obtained further important results on exceptional values by extending Borel's theorem to the simple and double a points of entire functions. The subject of exceptional values gained a fresh impetus with the outstanding contribution of NEVANLINNA, the creator of the modern theory of meromorphic functions. Around 1920, NEVANLINNA developed is a now well-known theory of meromorphic functions, which are the quotient of two analytic functions. Rolf NEVANLINNA founded its own value distribution theory to study the uniqueness problem of meromorphic functions and its derivatives, shared values, which are not important in the research topic. So in the early 1920s, Rolf NEVANLINNA, partly in collaboration with his brother Fritjof, extended the theory to meromorphic functions. NEVANLINNA theory, and also known as value distribution theory, is crystallized in its two main theorems, that is, first and second fundamental theorems. Qualitatively, the first one states that if a value is assumed less frequently than average, then the function comes close to that value more often than the average. And the second main theorem, it is more difficult than the first one tells. There are relatively few values which the function assumes less often than the average. This we will discuss later. Now let us come to the polynomials. So value distribution theory tries to answer the question of how many times does a certain function take a different value, complex values, and what is the distribution or density of these points. So we begin by looking at the simple case of a polynomial of degree n. This will serve to introduce the ideas of the theory and to suggest parallel a wider class of functions. By the fundamental theorem of algebra, f has exactly n zeros counted with multiplicities, or f takes the value 0 exactly n times. So on the other hand, we may ask how many times must f take any other complex value. So in this case, the polynomials, this is easy to see. We consider the polynomial f minus a, which is also of degree n. Then this polynomial takes the value 0 exactly n times. So that means f takes the value a exactly n times with multiplicities. This is clearly not true for a general real polynomial. So there are two things that this observation allows to deduce. Letting a1, a2 and so on an be the zeros of f, we can write f of z as c into z minus a1, z minus a2 and so on z minus an. And the meaning of this is any two complex polynomials with the same root can only differ by a constant. And we also have limit mod z tends to infinity, f of z divided by z to the power of n is equals to c. So more precisely, by the maximum modulus principle, we know that the value attained by f on a disk of radius r centered at the origin lies on the boundary. So we obtain the following statement about the growth of f. This is the statement: mod z tends to r, mod f of z is equals to order of r to the power of n as r tends to infinity. So we can say that the converse is true as well. That is, if the maximum modulus of a function grows as r to the power of n, then it is a polynomial. So we can see the interplay of the three distinct concepts here: the distribution of the zeros of a function, the growth of such functions, and what extent is the function determined by these zeros. So here we come to the most basic concept, that is analytic functions. A function f of z is said to be analytic if f dash of z exists finitely at every point of D. And also, if it is analytic at a point Z is equals to Z0, there exists a neighborhood of the point Z0 in which F is analytic. If F is not analytic, then Z0 is called a singular point or singularity of F. These are the well-known results, Taylor's and Lorentz theorems. So here, F is analytic in the interior of the circle with center alpha and radius r, and F of Z is defined by summation n is equals to 0 to infinity an z minus alpha to the power of n, where an is given by f to the power of n alpha divided by n factorial. And the Lorentz series, f can be represented by a series of the form f of z is equals to summation n is equals to infinity an z minus alpha to the power of n plus summation n is equals to 0 to infinity bn z minus alpha to the power of minus n. Here an is given by integral c f of z divided by z minus alpha to the power of n plus 1 into dz, and bn is given by integral c f of z divided by z minus alpha to the power of minus n plus 1 into dz. C is the circle with the center alpha. So again, we have zeros and singularities. F is analytic function with a singular point z is equals to alpha at z is equals to alpha. If there exists a neighborhood alpha which contains no other singular points, then alpha is called a isolated singular point or simply an isolated singularity of the. If alpha is an isolated singularity of F, then F can be expanded in the Lorentz series. So this is the Lorentz series expansion. We have already discussed some f of z is equals to summation n is equals to 0 to infinity an z minus alpha to the power of n plus summation n is equals to 0 to infinity bn z minus alpha to the power of minus n. R is the distance of the point from the nearest singularity of F other than alpha itself. You can observe here the portion of this series involving the negative powers. So the portion of the series involving negative powers of z minus alpha, that is summation n is equals to 0 to infinity bn z minus alpha to the power of n, is called the principal part of F, while the series non-negative powers or positive powers, so this is the positive powers of z minus alpha, is called regular part of F at alpha. So here we consider three cases. Case 1, suppose that all the coefficients of Bn are 0. Then we call z is equals to alpha is a removable singularity of F. Because so we can make F regular when mod z minus a is less than alpha by suitably defining its values. Similarly, if the principal part at z is equals to alpha contains a finite number of terms only, then F is said to have a pole at z is equals to alpha. If we consider Bm is the last non-vanishing coefficient in the principal part, then we write f of z in the form of summation n is equals to 0 to infinity an z minus alpha to the power of n plus b1 by z minus alpha plus b2 by z minus alpha whole square plus and so on bm by z minus alpha to the power of m. And the pole is said to be of order m. So here m is equal to 1, then we call it as a simple pole, and for m is equal to 2, it is a double pole. Similarly, next case, The principal part of f at z is equals to alpha contains infinitely many non-zero terms. Then z is equal to alpha is called an essential singularity of f. If the singularity is non-isolated, then it is called a non-isolated essential singularity. So f has a Taylor series expansion around alpha, which is of the form summation n is equal to 0 to infinity an z minus alpha to the power of n. If we substitute a naught, a1 and so on, ak minus 1 is equal to 0 and ak not equal to 0, then the above expansion takes the form f of z is equals to summation n is equals to k to infinity. So up to k minus 1 it is 0 and we start from k, that is n is equals to k to infinity an z minus alpha to the power of n. So in this case z is equals to alpha is called a 0 of f with the multiplicity k. For some finite complex number a 0 of f minus a. This above we defined 0 of f with the multiplicity k, and here a 0 of f minus a with the multiplicity k is called an a point of f with multiplicity k. So here a pole of f of multiplicity k is sometimes called an infinity point of f with again multiplicity k. If the function f has no singularity in the open complex plane, then f is called an entire function. If the possible singularities of an analytic function f are only the poles, then f is called a meromorphic function. So for example, a rational function tan z, cot z, 1 by e power z minus 1, etc. are meromorphic functions, and e power z, sine hyperbolic, cos hyperbolic z, etc. are entire functions. Here, a meromorphic function in the open plane may have infinite number of poles or zeros or a points, but there is only a finite number of them in any finite domain. Otherwise, there would exist at least one limit point of poles or zeros or a points in the finite plane, and this would be an essential singularity. Thus again, two cases may be distinguished. So case 1, the pole at infinity is a regular point or a pole. So here the function has a finite number of poles or zeros in this case. Case 2, the point at infinity is an essential singularity. In this case, the function has an infinite number of poles or zeros which accumulate at the point at infinity. The principal objectives of the value distribution theory is to study the behavior of the function f of z minus a is equal to 0 for an entire or meromorphic function f. So in this theory, we mainly investigate in which manner the roots of the equation f of z minus a is equal to 0 are distributed over the complex plane. So here the following results are well known. First result, if alpha is 0 of an analytic function f, then there exists a neighborhood of alpha which contains no other 0 of f unless the function is identical to 0. In other words, we can say that zeros of an analytic function are isolated unless the function is identically 0. Second result, a limit point of the zeros of an analytic function is an essential singularity of the function unless the function is identically 0. And the third result, a limit point of poles of an analytic function is an isolated essential singularity of f. So we consider a non-constant meromorphic function f and a complex number a which is finite or infinite. then the solution of f of z minus a is equal to 0 or isolated points. Also, we note that the boundary region, the equation f of z minus a is equal to 0 has only a finite number of roots, because otherwise f would have an essential singularity in the region, which is the limit point of the roots. Now we are in the position to state Poisson-Jensen's formula for a neuromorphic function, which is the gateway to the NEVANLINNA theory. So this is the statement of Poisson-Jensen's formula. So here, if we agree to count the poles are zeros according to their multiplicity, then we can drop P mu and Q nu from the above expression. So from this expression, we can drop this P mu and Q mu. This P mu and Q mu. This formula is deduced under the assumption that neither the poles B mu nor the zeros A mu are to be on mod z is equals to R. The theorem continues to hold if we permit zeros and poles on mod z is equals to R. So Rolf Nevanlinna developed a systematic study of the value distribution by means of first and second fundamental theorems. So to this end, we will explain some preliminaries of Nevanlinna theory. Firstly, we define positive logarithmic function log plus x is equals to log x if x greater than or equal to 1, and 0 if x is less than 0 is less than 1. Clearly, these are the following conditions holds, that is, positive logarithmic of alpha greater than or equal to log alpha, log plus alpha is less than or equal to log plus beta, provided alpha less than or equal to beta. Log alpha is equals to log plus alpha minus log plus 1 by alpha, and log plus of product of I is equal to 1 to p alpha I is less than or equal to summation I is equal to 1 to p log plus of alpha I. So here the term MRF is called proximity of function, which can also be expressed as MRF is equals to infinity. MRF is equals to infinity, or simply we can say that MR infinity. MR infinity, and is defined by 1 divided by 2 pi integral 0 to 2 pi log plus mod f of r e power I theta into d theta, and MR 1 minus a. MR 1 by f minus a is also denoted by MRF is equals to a. MRF is equals to a, or simply we can say that MRA. Simply we can say that MRA, and is also defined as 1 divided by 2 pi integral 0 to 2 pi log plus 1 by f of r e power I theta into d theta. Next we define NRF, the counting function of poles of f, and similarly NRF is also defined by NRF is equals to infinity, simply NR infinity, similar to MRF, and is defined by integral 0 to r ntf minus n0f divided by t dt plus n0f log r. Here ntf denotes the number of poles of f of z with multiple poles are counted according to their multiplicities, and n0f denotes the multiplicity of poles of f of z at the origin. And next we have NR 1 by f minus a, And we know that this can be denoted by NRF is equals to A, or simply NRA, and is defined by integral 0 r n of t comma 1 by f minus a minus n of 0 comma 1 by f minus a divided by t dt plus n of 0 comma 1 by f minus a into log r. So here n of t of 1 by f minus a denotes the number of zeros of f of z minus alpha, each zero being counted with its proper multiplicity. And n0 1 by f minus a is the multiplicity of the zero of f of z minus a at the origin. So here we have another important function, that is the characteristic function TRF, and is defined as TRF is equals to the sum of proximity function and counting function. So here MRF is the proximity function, NRF is counting function. The sum of proximity function and NRF is called the characteristic function. So clearly we say that TRF is a non-negative and it plays a cardinal role in the whole theory of meromorphic functions. And also we define TR1 by f minus a is equals to MR1 by f minus a plus NR1 by f minus a. And here TR1 by f minus a is said to be the characteristic function of 1 by f minus a. And we define the order of meromorphic function. So rho of f is the order, limit supremum r tends to infinity, log plus of TRF divided by log r. So here we have the following properties. N bar RF is less than or equal to NRF. So since we have N bar, we count multiplicity only once. NRF bar K, we write it as K into NRF. If it contains bar means we write it as only NRF. This K we won't write. So N bar R into F bar K is nothing but we are counting the multiplicity only once. Therefore, we write it as NRF. Since bar is not there, therefore NRF bar K is K times NRF. Similarly, we define MRF bar K and TRF bar K are respectively K MRF plus log 2 and K TRF plus log 2. Similarly, another property, NRF plus G is less than or equal to NRF plus NRG. And we define MRF plus G, which is less than or equal to MRF plus MRG, and TRF plus G is less than or equal to TRF plus TRG. Next one is TRF into G, again which is less than or equal to, we write NRF plus NRG, and similarly we define MRFG and TRF into G. So here another order, it is a lower order, is defined by lambda f. Lambda f is called the lower order and is defined as lambda f is equals to limit infimum r tends to infinity log plus TRF divided by log r. So also it is easy to see by considering the poles and the following inequalities. Log plus of xy is less than or equal to log plus x plus log plus y, and log plus x plus y is less than or equal to log plus x plus log plus y plus log 2. If we consider two meromorphic functions f1 and f2, then TRF1 plus f2 is less than or equal to TRF1 plus TRF2 plus order of 1. So the above results lead us to the following first major result in NEVANLINNA theory. So the first fundamental theorem, this is the major result in NEVANLINNA theory. So we have TR1 by F minus A is equals to TRF plus log of lambda plus epsilon AR. Here C lambda is the first non-zero coefficient at the origin of 1 by f of z minus a. and epsilon a r is less than or equal to log plus of mod a plus log 2, and we consider meromorphic function f, and a is the arbitrary complex number. So this is an equilibrium theorem, which is essentially state that f has no special affinity to any particular value. If f is meromorphic and non-constant, then TRF is larger when R is large, so that f takes the value a very often, or f is very close to a on the part of mod z minus a less than or equal to R. So this is another important result. For f is for a rational function f, TRF is equal to order of log R. So now we come to the second fundamental theorem. So this is an elegant deep theorem, which is the central art of NEVANLINNA theory. And because of this theorem, NEVANLINNA becomes a rich non-trivial theory. Before we state the second fundamental theorem, we state the following important lemma. So lemma of logarithmic derivative. For a transcendental meromorphic function f of z, we define mr f dash by f is equals to SRF. If f is a finite order, then mr f dash by f is equals to order of log R. And if f is infinite, then mr f dash by f is equals to order of log TRF plus log R. And R does not belongs to E naught. Here E naught is the set whose linear measure is not greater than. And we define SRF, which is the error term mr f dash by f plus mr f dash by f minus 1 plus log of f of 0 into f of 0 minus 1 divided by f dash of 0 plus log 2. So we take this as error term. And one of the important derivative, that is TRF per k. So kth derivative is less than or equal to TRF plus k n bar RF plus SRF. So combining, we can write TRF per k as k plus 1 TRF. So if you combine these two, we can write it as TRF plus SRF. TRF plus SRF. This follows from the lemma of logarithmic derivative and the properties of the characteristic of two functions. Now come to the second fundamental theorem via logarithmic derivative. So here we consider a non-constant meromorphic function f of z and a finite complex numbers aj for j is equal to 1 to q, and we define mrf plus summation j is equal to 1 to q mr aj less than or equal to 2 trf minus n1 of r plus srf. And here n1 of r is equals to 2 nrf minus nrf dash plus nr1 by f dash. The second fundamental theorem combined with the first main theorem immediately results in the following corollary. This is the corollary which, if we combine both the first and second fundamental theorems, we get this result. Suppose f of z is meromorphic in the finite plane, and we take the distinct numbers aj, j is equal to 1, 1, 2, etc. q. Here one of them may be infinity. We consider one of them may be infinity. Then we define q minus 2 TRF is less than summation nr1 by f minus aj minus n1 of r plus srf. The value distribution theory has several applications in many branches of mathematics. Here we state some of the consequences of second fundamental theory, and for this we introduce some notations. So this is the deficiency relation. We define delta a comma f. So here delta a comma f is called NEVANLINNA defect or deficiency of a with respect to f, and is defined by 1 minus limit supremum r tends to r nr1 by f minus a divided by TRF. And here theta A comma F is called as index of multiplicity, or the ramification defect is defined by 1 minus limit supremum r tends to r n bar r 1 by f minus a divided by TRF. And small theta A comma F, which is nothing but truncated defect, is defined by limit supremum r tends to r nr 1 by f minus a minus n bar r 1 by f minus a divided by TRF. If f of z minus a has no zero and a finite value a is called a Picard exceptional value. If f of z minus has at most infinitely many zeros, then a is called generalized Picard exceptional values. We consider a sharing value of two meromorphic functions f and g if and only if f inverse of a is equals to g inverse of a for f of z is equals to a and z belongs to g of z, which is equal to a. The most fascinating result in this direction is the following 5-point theorem of NEVANLINNA. So before going to state the theorem, we introduce some of the notations. So these two are the most important notations of NEVANLINNA. We say f and g share a counting multiplicities. Simply, we can write it as ACM, provided that f minus a and g minus a have the same zeros with same multiplicities. Here f and g are non-constant and a is a finite number. Similarly, f and g share a ignoring multiplicities, or simply we say that AIM, provided that f minus a and g minus a have the same zeros ignoring multiplicities. So this is the statement of 5-value theorem. We consider 5 values for j 1, 2, 3, 4, 5. AJ ignoring multiplicity, share ignoring multiplicity, then f is equivalent to g, where f and g be two non-constant meromorphic functions. And AJ is the 5 distinct value in the extended complex plane. So here it is natural to ask what will happen in a special case when g is equal to f dash in 5-value theorem. So based on this curiosity, the matter on sharing values between entire functions and their derivatives was developed, which was first studied by Rubel and Yang. So analogous to the NEVANLINNA's 5-value theorem, in the early 1977, Rubel and Yang proved that if any non-constant entire function f and its derivative f dash share two distinct finite values a and b counting multiplicity, then f is equals to f dash. So after 2 years, 2 years later, Muse and Steinmetz proved that actually in the result of Rubel and Hang, one does not even need the multiplicities. So later it was shown in general the results of Rubel Hang or Muse Steinmetz are false if f and f dash share one value. Thus one may ask that what conclusion can be made if f and f dash share only one value, and if an appropriate restriction on the growth of f is assumed. So in this direction, a famous conjecture was proposed by Arbrecht in 1996. Since then, the conjecture and its analogous results have been investigated by many researchers. And we define one of the important definition, differential polynomials and monomials. So here n0 j, n1 j and so on, n k j be a non-negative integers, and we have the expression mj of f is equals to f to the power of n0 j f to the power of 1th derivative n1j and so on to the power of kth derivative to the power of nkj is called differential monomials generated by f of degree. So here degree is defined by dmj, weight is defined by gamma mj, where dmj can be written as d of mj and is defined by summation I is equals to 0 to k nij. Similarly, the weight gamma mj is equals to summation I is equal to 0 to k I plus 1 into nij. And the sum, so the sum we take it as p of f, which is defined by summation j is equals to 1 to t j mj of f and is called a differential polynomial generated by f of degree d bar p. So here we define degree by d upper bar p, which is maximum of dmj, that is dmj 1 is less than or equal to j less than or equal to t, and weight is defined by gamma p, which is equal to maximum of gamma mj 1 is less than or equal to j less than or equal to t, where TRBJ we write it as SRF for j is equals to 1, 2 and so on t. The numbers d lower bar p. So here we defined upper bar and here d lower bar p is equals to minimum of dmj, where j is in between 1 and t, and k be the highest order of the derivative of f in p of f, are called respectively the lower order and order of p of f. So this is called d lower bar p is called a lower order, lower degree, and k is the order of p of f. So we define highest order of the derivative of f in p of f are called respectively lower degree. So d lower bar p is called a lower degree and k is called the order of p of f. So the differential polynomial p of f is said to be homogeneous if d upper bar of p is equals to d lower bar of p. So d bar p is equals to d lower degree of p, then we call it as p of f is homogeneous. Otherwise, p of f is called a non-homogeneous polynomial. So the value distribution theory of meromorphic functions occupies one of the central places in complex analysis. Numerous works are devoted to studying its connection with other areas of mathematics such as topology, differential geometry, measure theory, potential theory, and others, extending its inferences to wider classes of functions. Wider classes of functions, for example, meromorphic functions in arbitrary plane regions and Riemann surfaces, algebraic functions, functions of several variables, also meromorphic curves, and also its applications mainly to the analytic theory of differential equations. NEVANLINNA theory had emerged as a powerful tool in the study of meromorphic functions, normal families, complex differential equations and difference equations, etc. So in the theory of differential equations, in many cases, it is impossible to find an explicit solution of a given differential equation. But NEVANLINNA theory offers an efficient way for this problem. The only requirement is that the solution must be meromorphic either in the whole complex plane or in the small domain where the growth of solution is sufficiently large near the boundary of the domain. And H, which in 1942 was the first to make the systematic study in the application of NEVANLINNA into the complex differential equations. Now later, due to the efforts of S. Bank, Lipolane and others, NEVANLINNA theory became the leading tool in analyzing solutions of complex differential equations. So, another important application of a lemma of a logarithmic derivative in complex differential equations. It has many useful results in NEVANLINNA theory and a huge number of applications in the theory of ordinary differential equations. And for instance, we can say that Yoshida's generalization of Malmquist theorem. So this is one of the generalization theorem. It depends heavily on lemma of logarithmic derivative. So in contrast to differential equations, nonlinear differential equations often admit neuromorphic solutions, and hence NEVANLINNA's distribution theory is applicable. The foundation of the theory of complex difference equations was led by Nolan, Julia, Bikoff, Batchelder, and others in the early part of 20th century. So later on, Yanagihara and Lane studied these nonlinear complex difference equations from the point of view of NEVANLINNA. Another application in the connection between NEVANLINNA theory and the Diophantine approximation. So, which is goes much deeper in the connection between NEVANLINNA and Diophantine. One of the mathematician, Paul Orza, expressed in great detail in the analogy of between the theory of NEVANLINNA and Diophantine approximation in the year 1987. He showed that many of the functions of NEVANLINNA theory have corresponding functions. Corresponding functions are quantities in Diophantine approximation. And moreover, that there existed theorems analogous to the first and second main theorem. And these are some of the percent of time. I have given some of the basics growth of NEVANLINNA theory and its simple applications. I stress here that NEVANLINNA theory find greater applications in the field of mathematics, and I advise the audience to pursue this field so that you can contribute substantially in the above areas by the use of value distribution theory. So thank you, Nadu. So first of all, let me thank the organizer of this webinar. Especially, I'll thank Venkataramanan sir for giving me opportunity to speak here. So I also suggest that the organizer hold more and more of such seminars so that there will be a fruitful interaction between teachers and students, especially given in the present pandemic situation. So audience here are the paramount to the success of any webinar. Without them, the webinar will lose its aim and purpose. So I thank you for giving a patient hearing. Thank you, Nadu. Any questions?
Thank you, ma'am. Thank you. So far, no question is posted in the comment box.
I think
But
this
anyhow,
is new to everyone. So,
ma'am, can you explain in students aspect how this can be applicable? It is a deviation of what part of complex function? Can you explain so that they can be able
this
to
is
know?
so this is extension of complex analysis, sir. So after entire and neuromorphic, up to entire and neuromorphic, and up to maximum modulus, you have studied in BSc or MSc. This is further extension by NEVANLINNA. So only for research purpose and only the application part of mathematics, we can study this NEVANLINNA theory. But in real, we can't apply this NEVANLINNA theory. So far, no one has applied in real life this NEVANLINNA theory. Even we are searching for that.
Okay, okay. Thank you, ma'am. Thank you, ma'am.
Yes, sir.
Thank you for your enlightening talk. Hope this eye-opening session on NEVANLINNA theory can impact positively among the participants who can further work on it and can learn much on it. Thank you, ma'am.
Thank you, sir. Thank you.
Saying thank you is more than good manners. It is good spirituality. Now I invite Mr. P. Thirumal, Assistant Professor, PG and Research Department of Mathematics, DG Vaishnava, to deliver vote of thanks. Thirumal sir.
I'm very grateful and honored to propose a formal vote of thanks on behalf of Postgraduate and Research Department of Mathematics, DJ Vaishnav College, to all who spared their valuable time to make this national webinar with title National Webinar on NEVANLINNA Theory and its Applications, organized by our institute. I thank our most distinguished resource person, Dr. Rajeshwari S., Assistant Professor, Department of Mathematics, Presidency University, Bangalore. We are sincerely astonished with your presentation, madam. Once again, I thank our resource person. We are thankful to our beloved secretary, Sri Ashok Kumar Mutra, for his motivation. I would like to thank our respected principal, Dr. S. Santosh Babu, for his enthusiastic support. My sincere thanks to our head of the department, Professor R. Venkatramanan, for organizing this webinar. A special thanks to the organizing committee, faculties of our department for their unconditional support and coordination. Our heartfelt thanks to all the participants. Feedback link posted in the chat box. And I'm happy to inform about our next webinar titled Discrete Fractional Calculus. Resource person Dr. G. Brito Antoni Xavier, Associate Professor, PG and Research Department of Mathematics, Sacred Heart College, Tirupattur, which will be held on 6th March 2021, 10:30 a.m. to 12 noon. With these words and happy fulfillment, we move to the end of the webinar. Thank you.